what we do is we have to understand that we're at STP, we're given moles, we're asking for volume. So that's a, and then they tell you that you're at, I've already said this, but at STP, that's the most important thing here, because what you do is you take, all right, come on, there we go. All right, so you take the, I think it was like 0.68 moles of oxygen gas. We want to convert this to liters of oxygen gas at STP. So what we have to do is we have to understand, okay, first of all, we can do this in two different ways. Let's do this the easy way. So what we're going to use is 22.4 liters per mole. All right, and so we set up a conversion factor here, all right, the dimensional analysis chart. So we have 0.680 moles of oxygen gas. And so what we do is we have to convert to liters. So we want this to be on top. So we're going to put 22.4 liters per mole. The moles cancel out. All right, so all we have to do now is a simple algebra here, just multiply across. So we take 0.68 times 22.4. And so what we have here is 15.2 liters of oxygen gas. All right, and so that's easy. All right, great. So that's the shortcut way. Now, the other way, we talked about this the other day with the ideal gas law. We can input information in. You say, well, we don't have everything we need. Yes, we do. All right, we have STP given to us. Remember that standard temperature and pressure. So the temperature is 0 degrees Celsius, which is also 273 Kelvin. Always make that conversion factor. You have your pressure, which is 1 atmosphere. If you guys can hear my dog whining, that's because she's laying beside me, but she don't like the fact that she's laying beside me, so she wants to whine. She wants to get down and go see my wife, who is her adorable person she wants to be around. Yeah, I'm telling them all about your whininess. Yeah, so you want to be quiet for a few minutes? Just enjoy our chemistry lesson? You can learn about gases. Oh, you're filled with hot air, I know. You're expelling it right now, you big whiny butt. All right, can I teach? All right, you go on. Yeah, just go on. Go back to mom. She's coming back to you. All right, we're going to use the ideal gas law. PV equals nRT. I'm so sorry about that, guys. That's the problem with working from home. You got whiny dogs. They always want attention, but then when you give them attention, they want to cry because they don't want your attention. All right, so pressure is 1 atmosphere. And if you're not laughing at that, I can't help you. I'm sorry. Moles is 0.680. And then your R, 0.08206. And then your temperature is 273 Kelvin. So we're just going to solve for volume. All I can do is divide out the pressure, which is 1 atmosphere as it is. So we're going to take 0.68 times 0.08206 times 273. That gives me 15.2 liters. Well, I'll be a son of a gun. We had the same thing happen the other day. We get the same answer. Well, which way do you think is the easiest way? Think, Sydney, which way do you, well, can you talk first of all, Sydney? Or is it chaos at your house today? All right. So, yep. Okay. All right. So we're using STP. Yep. All right. What did I say? How many? Which way do y'all want to do it? Y'all want to use the ideal gas law, or do y'all think the molar volume would be easier? Yeah, it's always that, Devin. If you're at STP, that 22.4 liters per mole is a standard. That's why we call it standard temperature pressure, STP. Yep, no problem. No problem. Oh yeah, it's definitely easier. You're the Devin. Thank you for talking to me because nobody else is talking to me. Catalina, Josephine, Christine, Grace, Kinsley, you guys all with me today? All right, great, great. Okay, yeah, that's all I want. Just to make a simple comment. Which way do y'all want to, Grace? Which way do you like doing it? Do you want to do it the ideal gas law, or would you rather use the 22.4 liters per mole? Yeah, I do too. It's a lot easier. But the point is that if you don't remember to do the 22.4 liters per mole, it's not the end of the world because guess what? You can fall back on the ideal gas law. So remember, the ideal gas law is a very important equation. It's one that you can use. So, right. All right, now let's see here. So going back to the notes here. So our other problem. Now I was using 0.68, but still same concept. I used 0.068 in the guide here. Now, example 2 says a chemical reaction produced 98.0 milliliters of sulfur dioxide gas at STP. What was the mass in grams of the gas produced? So, what we need to do is convert your milliliters into liters. That's the first thing you always do, convert milliliters into liters. Because if you use the ideal gas law, it has to be in liters. So in the same concept here, the molar volume has units of liters, so you have to convert. Make a note of that right now, okay? Say it right on your notes. Make sure you convert your volume from milliliters into liters into discussion. Now they tell you STP, great. That tells us that we are going to use molar volume. What was the mass in grams of the gas produced? Now, first thing we got to do, milliliters to liters, and then convert liters into moles. All right, so 98 milliliters dividing by 1,000 is going to give you 0.098 liters. So then we're going to multiply that by, so for every mole you have 22.4 liters. So the liters cancel out. All right, so 0.098 divided by 22.4. That gives me the 0.0044. Well, let's do this to 3 sig figs. So 0.00438 moles of SO2. Now, the next thing you want to do is convert your moles of SO2 into grams of SO2. We did the molar mass of that. So we have 32 plus 32. This is oxygen, and this is sulfur. That's 64 grams per mole. So we have 0.00438 multiplied by 64 grams per mole. And so your moles cancel out here, and you end up with grams. So 64 times 0.438 gives me 0.280 grams of SO2. And that's it. So that's the answer for that problem. So just a little recap here. So we're getting volume at STP, and they tell you that it's STP. That's important. So convert your milliliters into liters, and then we divide it by the molar volume, which gives us our moles of sulfur dioxide. Figure out the molar mass, sulfur dioxide, multiply by that, and you end up with the grams of SO2. Any questions on that? Yep, I used 0.68, Cassandra. I changed the number just slightly. So if you look back up here, I used 0.68, whereas in the notes it was 0.068. Yeah. All right. Thanks, Sydney. So does anybody have any questions about this problem that dealt with sulfur dioxide? Does everyone follow the process that we go through solving for? Who is this L person live? Sid. Who is that? Obviously it's someone in class. How in the world did y'all get into class with that name?
I don't know. I thought it might be me because I joined on the second device.
Yeah. Well, they're not obviously gonna talk or anything. Well, interesting. Y'all let me know if something happens. Yeah. Well, all right. If something blows up, I don't know what to do. Okay, so Dalton's law. Let's do Dalton. So Dalton's is very easy. Y'all know how to add, right? That's all Dalton's law is, just adding the individual pressures of gases. So P total is equal to P1 plus P2 plus P3. Now P1, P2, and P3 are the partial pressures of individual gases that are present in a mixture. So the best example that I can tell you of right now is the Earth's atmosphere. So we all understand the atmosphere. It's important. What's in the atmosphere? A lot of gases. So here's Earth, and here's the atmosphere above Earth. Look, it almost looks like an egg here. Let me put Earth here. All right. So, well, what gases are in this atmosphere? Well, there's nitrogen gas, which makes up 78%. There's oxygen gas, which makes up 21%. And then there's all the other gases, which makes up roughly 1% of the atmosphere. Now, if you add that up, that's going to be what, 22, that's going to be 100%. So one thing that we can do is we can measure the atmospheric pressure. Now, knowing the percentages of the individual gases, we can actually figure out the partial pressure. So for today, I'm going to look this up right fast on my phone here. So what is the pressure atmospheric pressure today? So right now it's roughly 30.27 inches of mercury. So in this example, we really don't have to convert to atmospheres or anything like that. We can do that, and I think that might be a good exercise, but I'm not going to do that right now. So what I want to do is I want to figure out the pressure of nitrogen gas. So what I do is I take the percentage. Now keep in mind that inside of percentage, so we need to divide this by 100. So 0.78 divided by 100 gives me 0.78. And so I'm going to multiply that by 30.27 inches of mercury. And what that does, it'll give me the partial pressure for nitrogen gas. And so that ends up giving me 23.61 inches of mercury. So I want to carry this out to 2 decimal places because of my unit here. So it's 30.27. I want to try to keep that consistent here. Even though my 0.78 is two significant figures, I'm going to keep the pressure as constant as I can. That way they all match up. So the pressure of oxygen gas is going to be 0.21 multiplied by 30.27. So 0.21 times 30.27, that gives me not that answer. That gives me 6.36 inches of mercury. All right, so that now we're going to figure out the pressure of the other gas. So other gases include everything else. So really the bulk of our atmosphere is composed of nitrogen gas and oxygen gas. And this is at sea level, of course. All right. So our percentage of oxygen right here where we live is right around 19 to 20% roughly. So 0.01 multiplied by 30.27. That is going to give me 0.30. Yeah, so 0.30 inches of mercury. So I'm going to add these together. Dalton's law is where you take the total pressure is equal to P of the pressure of nitrogen plus pressure of the oxygen plus pressure of the other gases. So 23.61 plus 6.36 plus 0.3, that gives me 30.27 inches of mercury. So wow, look at that. It is perfect. So that's what we wanted to have. So that's a good example. It's a great example of, looking at a system, figuring out what the individual gases are, and then figuring out, the partial pressures of each of those individual gases. So now one other thing we can do with this is we can figure out mole fraction or just in general, a ratio of the gases. And so looking at the lecture notes here, all right, you end up, so you can see right here, you have the ideal gas law, all right, where you can still apply it, where we figure out the individual pressure of each gas based off the moles, the variable there are any other variables here, the temperature and volume. And so you can figure out, like I keep saying, ideal gas law is an important gas law. So the ideal gas law can be used in many different ways in this chapter. And so this is just another way we can utilize it, and we can figure out the individual pressures. Now, the good thing about the example that I just showed you is that we know percentages. So we actually took the percentages of the gases and used them to figure out what the partial pressure of each individual gas is. And so not always will it be like this. So let me give you an example here. So our example we're going to look at is right here. All right, and I'm just going to stay on this page. So it's dealing with a scuba diver, and scuba divers, first of all, scuba diving, you have to go down underwater. And so if you've ever went swimming, I'm pretty sure all of you have gone swimming. One of the things that as a kid, this is what I remember, I always liked to try to dive as far as I could down underwater to see if I could touch the bottom of the swimming pool. And it takes a lot of effort to do that because as you go down underwater, the pressure of the water builds up on top of you, and you actually can feel it. You can sense in your ears because it'll make your ears pop. How many of you have had that happen before where you've gone swimming and you dive down, but you can, as you go down, you can feel the pressure pushing down to your body? Some people can handle it, some people cannot handle it, so it just depends on who you are. So what a scuba diver does is that it has oxygen gas and it also has helium gas. And what that does is it helps you to prevent from getting a condition called the bends. Now, if you don't know what the bends is, that's something you can look up later. I YouTube it and watch a little documentary. It will, just so you have an idea what a bends is. If you ever decide that you want to be a scuba diver, this is something you have to take consideration. If you come up too fast, what might happen is would have an imbalance in your blood, and that could cause you to have, be poisoned. So what they do, if you do develop the bends, they have to put you in a pressure chamber, and you have to stay in that chamber for a day or so or more, depending on how bad the situation is. And that way it equilibrates your body back to the conditions that you normally live under. And so, anyhow, let's keep moving. So, for a particular dive, 46 liters of helium at 25 degrees Celsius in 1 atmosphere, and 12 liters of oxygen at 25 degrees Celsius at 1 atmosphere were pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius. So before we do anything, we're not given moles of helium and we're not given moles of oxygen. So you're saying, well, how do I know to do that? All right, well, you look at the information that they give you. In order for us to figure out the partial pressure of each gas, we need to know the moles of gas. That's the first thing, because we're going to have to use the ideal gas law. So you have liters, temperature, and pressure, and we're solving for mole. So that's ideal gas law by definition. So figure out the moles. We're going to set the equation up just like this. So each gas has its own set of conditions. So helium, the pressure was 1 atmosphere. The volume was 46 liters. So that's what's going to change here. It's the volume. The R constant doesn't change. The temperature was 25 degrees Celsius. That doesn't change. But notice that it's 298 Kelvin. Don't bring the Celsius, bring the Kelvin temperature down. So doing the math here, you'd have on top 1 times 46 divided by 0.08206 divided by 298. And that gives you 1.9 moles for the moles of helium. All right, great. So now let's do that for oxygen. So we look at oxygen. Oxygen is at 12 liters. So notice that these three stay constant, but the volume changes. So we just change out the 46 to 12. We go through the calculation of 1 times 12 divided by the bottom, and we get 0.49 moles of the oxygen gas. All right, so I told you a minute ago that we need the moles of the individual gases so we can figure out the partial pressures. All right, so we've got our moles. Now we're going to go back and we can utilize the ideal gas law again. This time we know our moles, we plug that in, but the difference is the volume of the gas tank is 5 liters. So it's pumped into a tank with a volume of 5 liters. So our volume is now going to change to 5. So we're plugging this in. You got your N from up here. Your R is a constant. The temperature is 25 degrees Celsius. That did not change. However, the volume does change to 5 liters. So we input that information into the gas law, and we end up with 9.3 atmospheres for helium. And we do the same thing for oxygen. Again, the volume is 5 liters, and we end up with a pressure of 2.4 atmospheres. So those are the individual pressures. Now, they want you to calculate the partial pressure of each gas and the total pressure. So to figure out the total pressure, all we're going to do is add these two together. So 9.3 plus 2.4 gives me 11.7 atmospheres. So that would be the total pressure in the gas tank. Are there any questions on that? Now, I'm sure that you guys are looking at, your heads are spinning right now. But just keep in mind that it's nothing that's really new other than the fact of we're applying Dalton's law using the ideal gas law. All right. So questions, y'all have any questions for me? Feel free to say yes or no.
So this doesn't really have to do with the topic at hand, but I was wondering, I was having a conversation with a friend about this. Is it not possible to synthesize ozone and then just put that into the atmosphere, in place of like the ozone that's lime? Sorry, that's totally off topic, but
Probably not. I don't think this synthesis of ozone is very easy to begin with because ozone is O3. So you have to take oxygen, which is O2, and reacting it with a monatomic oxygen. And to produce a monatomic oxygen atom is not easy to do. It's not going to be very stable because think about the fact of this is kind of off topic, but rust. If you put an piece of iron outside and you leave it overnight and that iron gets exposed to moisture from the air, what's the iron going to do as a result of that exposure? It's going to rust. Now, going back to your ozone, oxygen is very reactive. It's going to react easily. If you have a monatomic oxygen, it's not going to, if it's not the right conditions, you're not going to produce ozone. You're going to produce an oxygen gas molecule. And so producing ozone to put back in the atmosphere, when ozone itself is it's stable, but it's also unstable because O3, it's not going to be very feasible. You would spend more money trying to make it than what it would be worth. And think about how much space, how much volume of ozone you would have to produce to fill those voids. So that's what we have to look at there. And unfortunately, once that damage is done, you can't reverse it as it is. So that's why we don't use those fluorocarbons, the freon gas anymore. We use other types of freon gas that's less invasive on our atmosphere. And I'm assuming that's what you're referring to, right, Devin?
Yeah.
Yeah. All right. Hopefully, I wasn't too much information. Did you follow that, Devin? I know everyone else is like, "Oh my gosh, what are we doing here?" So, but does that answer your question?
Yeah, no, that makes sense.
All right. Thanks for asking. Okay, mole fraction. So mole fraction is using this symbol chi. All right, so you can see there, and we'll blow this up here. So it's a chi. It's like a weird looking X. So chi is equal to the moles of a gas. So one could be oxygen gas divided by the total moles of the system. All right, very simple. It's a ratio. So we could figure out the fraction of. Hang on a second. Sorry. We could figure out the fraction of the atmosphere using this. Now, we already know the percentage, so that's not really something we need to do, but I'm going to do it anyhow, all right? So we know that the pressure, so let's just figure out the mole fraction of nitrogen, okay? So the mole fraction of nitrogen, what I do is I look at the partial pressure of nitrogen, which was 23.61, okay? So I take the 23.61 inches of mercury, and I'm going to divide it by the total pressure, which was 30.27. And this would be the same thing as if I were to use moles. You're going to get the same answer regardless. So I don't have to use moles in this case. If you have the partial pressures, by all means, keep it simple. Use the partial pressure. So I'm going to take 23.61 divided by 30.27. And so I end up with, well, it should be this, but I'm going to end up with 0.78 for my fraction. And that's what it should be because the nitrogen's 78% in the atmosphere. So it's going to have a mole fraction of 0.78. And so oxygen gas would be 0.21, and then the other gas would be 0.01. All right, so other, and then oxygen. All right, so that's mole fraction. It's very simple to follow that. Hopefully that makes sense. All right, so now I do want to point this equation. Okay, so you notice that you can use the partial pressures, which we just did, or if you're given moles, you can use the moles. All right, so this equation down here that's at the bottom, P total times the mole fraction of 1. Now 1 again is the whatever gas you're looking at and studying would be equal to the partial pressure of that gas. So we could do that with nitrogen again. So if I know the total pressure is 30.27. So if I want to figure out the pressure of nitrogen gas, utilize it. So I know the mole fraction is 0.78. I'm going to multiply that by 30.27. And that will end up giving me, so 0.78 times 30.27, that gives me 23.61 inches of mercury. All right. So, and you can see that that's what we started with. And so it should make sense that these equations are just a cycle process. It's just basically using your math skills that you've learned over time and apply them to mole fraction, partial pressure, total pressure versus the mole fraction. So, are there any questions on these three equations and how to use them? Are there any questions? Please chat in the chat box if you have any questions. Just make a comment, yes or no. Are y'all good with this? Does that make sense? All right. Thanks. All right. Good. All right. So continuing on here. Now I'm going to stop at a certain point. We're not going to do real gases today. I don't want to do that. I think what we're going to do is we're going to get through root mean square velocity. I'm going to save Graham's law and real gases for Wednesday. If you want to go ahead and read up on those, that would be a good thing to do. Use your textbook for that, but let's talk about root mean square velocity. Now, you're going to have to know this derivation. I'm going to ask you on a test how to do this. So, and you're going to have to know what each individual part represents. So go ahead and write this down. Well, why do we need to write it down, Mr. Shelton? It's already on the screen. Thanks for asking that question, Sydney, because you just got to do it. Now, long story short, this is all you need to know. So let's take that over here. And you don't have to learn the derivation, by the way. I was just messing around. Root mean square velocity. So it's represented by this little symbol. This is a mu symbol, if I can write it correctly. So that's mu. So that just means average. So you get this little bar, it means average. It's equal to the square root of 3 RT divided by MW. R is the gas constant, and you're going to say, is it 0.0206? No, it's not. I'm going to change it up on you. 8.314 joules per mole times Kelvin. T is the temperature in Kelvin again. And MW is the molar mass. Now, keep in mind that you normally figure out molar mass in grams per mole, but in this case, you're going to have to convert to kilograms per mole. Sid, come here. Sid, come here. Are you crying because she won't let you in the room? I'm sorry. Why don't you lay down right here? Come on, lay down. There you go. Good girl. All right, so now how fast does a molecule move? You can calculate it. We can figure out the average root mean square velocity. So we can look at a couple different examples. Hydrogen gas versus methane gas. So we go about doing it. So the first thing we're going to do, let's go ahead and figure out the molar mass of each of these, okay? So the molar mass of hydrogen is 2.016 grams per mole. The molar mass of CH4 is 16 grams per mole. And I'm doing a little bit of rounding there. All right. Now, what's next? So the first thing I'm going to do is we see that the molar mass needs to be converted in kilograms per mole. So just divide these two numbers by 1,000. And so that's going to give you 0.002016 for hydrogen kilograms per mole. And then this one's going to be 0.016 kilograms per mole for methane. So let's figure out the root mean square velocity for hydrogen. So for hydrogen, we're going to do the square root of 3 times, all right, so the R is 8.314. The temperature, so we're going to say that these are at 25 degrees Celsius just to keep it simple here. So that's 298 Kelvin. And we're going to divide that by the 0.002016. So y'all go ahead and do that calculation. All right, Devin, what do you get for your answer when you do the calculation?
I haven't finished putting it through just yet. Give me half a second.
All right. Well, there goes a half a second. You got it now?
Not quite yet.
Okay, well, I'll give you 5 seconds. 1 potato, 2 potato, 3 potato, 4 potato, 5 potatoes. Got it? Still working on it.
Should I be putting this in? Oh, I
Just
didn't square root it.
Just tell me the number. What did you get on the calculator?
Um, 1,920.
Yeah, that's good. Now, anybody know the units for velocity?
It's meters per second, right?
Yeah. So that's the units for root mean squared velocity. All right, so it's meters per second. Now, if you are curious as to why it's in units of meters per second, I'm going to make a little, I'm going to teach you something. So joules is kilograms meters squared per second squared. So if I replace that into the parentheses there with the R constant, the kilograms is going to cancel out here. So this kilograms is going to cancel. Now your moles cancel here. Your Kelvin cancels here. So that leaves you with meters squared per second squared. If you take the square root of meters squared per second squared, you end with meters per second. That's why the units work out right now with this. So that's something important that you want to make a note of. All right, so let's look at CH4. So this stays pretty much the same. The only difference is now you're going to be changing the molar mass to 0.016. All right, so we should see a change here. We will see a change. The question is, how much change are we going to see? All right, so when I plug this in, okay, I have to input the right number here. There we go. Now we got it. All right, so when I input this into the calculator, what I end up getting is 682 meters per second. And so what you see is that the the lighter molecule, hydrogen gas, is going to move much faster through space than the CH4 molecule is going to move. And that should make sense. All right, so that's a great example of root mean square velocity and how to calculate those two. So what I want to do is look at two different graphs, okay? The first graph represents molar mass, okay? So the dependency of molar mass. So hydrogen versus methane. So methane would have a graph that looks like this, where the average right here, when you come down, that's where you end up with roughly 628 meters per second. So this is a fraction. The y-axis is fraction. This is in your textbook, by the way. You'll see it there. And then you have hydrogen gas, all right? Now, hydrogen gas is a little bit faster. So here's your average coming down. That's going to be roughly 1900 meters per second. So what you see here is that hydrogen is very dispersed. It's very broad because the velocities are so spread out. And so, but the average speed is faster for hydrogen gas. Now, to take that in comparison to methane, it's a lot less broad because everything's condensed in one place. It's almost like summertime, okay? In the summertime, you go to the beach, there are hundreds of people on the beach. They're all widely dispersed all across the beach. Go to the beach in December. How many people are you going to see on the beach? It's cold. There ain't many people out there. There might be 5 people at most. You can count them on one hand. So same concept here. So when it's hot, things get dispersed real fast. The molecules, there's a wide distribution of them. But when things are cold, where do you find people at? You find them inside, concentrated, where the heat source is found. So same concept. We are just like, we're living molecules, big molecules. We live under the same principles and rules that these molecules live under, even though they're gases. So this is dealing with molar mass. This is pertaining to the size and how heavy the molecule is. Now, as I start talking about temperature, so that's going to be the next thing. So we're going to look at just hydrogen gas, okay? So hydrogen gas only, but we're going to look at 25 degrees Celsius versus 100 degrees Celsius. Now, keep in mind that this is going to be 298 Kelvin, and then this will be 373 Kelvin. So we're going to see the same pattern. At 25 degrees Celsius, you're going to see a curve that looks like this because it's a cooler environment. Molecules are going to be more condensed together as compared to 100 degrees Celsius, which would look like this. So this is 25 degrees Celsius. This is 100 degrees Celsius. So does that make sense, everyone? All right, you can see a wide distribution. You can calculate this using the root mean square velocity. Remember that root mean square velocity is equal to square root of 3RT divided by MW. And so we're looking at the temperature aspect here. If I increase the temperature, I'm going to increase the root mean square velocity. It's just a mathematical operation. Okay, so I am going to stop recording.